Yeah.
So the next speaker is Professor Balcan from Georgia Tech.
All right. So since actually so our first speaker Avrim talked already about approximation stability, I decided to talk about something very different. This is a more machine learning or learning theory topic. I still think it fits the workshop theme, but in a bit of a different way. All right, so I'll be talking about semi-supervised learning, which is a modern learning paradigm, and I'll present a theoretical model for reasoning about semi-supervised learning. But first, I will start with a bit of background about machine learning and about the classic paradigm of learning from labeled examples only. All right, as you probably all know, as a research field, machine learning is concerned with designing programs that adapt from experience, and is incredibly useful in many areas of computer science and science more generally, in many applications such as image classification, document categorization, spam detection, and so on. And now classically, many of these problems have been modeled by using the supervised learning paradigm, which is actually one of the most important paradigms in machine learning, and which is also very well understood at the foundational level. So as a concrete example of a supervised learning problem, imagine that we are trying to write a computer program to help us decide which email messages are spam and which are important. Right, so what we want to do is to design a learning algorithm that takes as input a training set, a set of email messages labeled as spam or not, and produces a good prediction rule for future data, for future messages. And this is called supervised classification, since the learning algorithm uses labeled examples, in this case labeled emails, so email messages labeled as spam or not. Now, the very first step is to represent each message by a set of features. And for the spam problem, we might design features based on keywords, spelling characteristics, and so on. And here we have an example of a training set in the feature representation. So each row represents an email, a labeled example, an email message labeled spam or not. And so this is the labeled part, this is the unlabeled part, or the feature part of our example, and this is the labeled part. And now, given this specific data set, some possible reasonable rules that are consistent with the data, some good rules that are consistent with the data are predict spam if unknown and man your peers, or if you want to think of yes here as being 1 and of no as being 0, then this rule right here would also work, and this is an example of a linear separator in this feature representation. Now, of course, our goal is to come up with a rule that does well on new examples, on new data, on new emails, and not only to produce a rule that does well on the training set, right? And this brings up two important aspects in supervised machine learning and machine learning more generally. The first aspect is the algorithm design aspect. How can we automatically generate rules like those that I had on the previous slide that do well on the training set? And the second aspect is the confidence bounds or generalization guarantees aspect. What kind of confidence we have at rules that do well on the training set will also do well in the future. And now for the supervised learning setting, there are two very nice frameworks that allow us to talk about these aspects formally. And these are the statistical learning theory framework of Vapnik and the PAC model of Valiant. And formally, in these frameworks, we assume that the training examples, which could be, for instance, a set of labeled emails if we do spam detection, or a set of labeled images if we want to do image classification. So formally, we assume that these labeled examples are drawn IID from some fixed but unknown distribution over the instance space, and they are labeled according to some fixed but unknown target function. And then our goal is to do some optimization of a training sample, and in order to find the hypothesis H, and we want our hypothesis to have small error rate over the whole distribution. And for this talk, the notion of error rate that I'm using is, we define the error rate of a hypothesis H as being the probability that X predicts differently from the target function on a random example drawn at random from our distribution. Now, the case, so the hypothesis H that we find comes from some concept class C, from some hypothesis space C. The case where the target function itself is in the concept class C is called the realizable case. And the case where the target function is not in C is just called the agnostic case. All right, so this is the formalism for passive supervised learning, and in this setting, the sample complexity aspect is really well understood. And again, by a sample complexity statement here, I mean how many labeled examples do we need to see in the training process in order to be confident that the rule that does well over the training data will also do well in the future. And here is a very simple example of a sample complexity statement that works for the case when C is finite and for the case when the target is most meaningful in the realizable case. So what we can say is that if the number of labeled examples that we see in the training process is roughly 1 over epsilon log of size of C plus log 1 over delta, then with high probability, all the hypotheses of zero empirical labeled error rate will have true labeled error rate at most epsilon. So in other words, after we see so many examples, all the bad hypotheses, all the hypotheses of error at least epsilon will be inconsistent with the data. Now this is for the case when C is finite. When C is not finite, we just need to replace log of size of C with this dimension of the concept class. And for all we know, actually, we also have to lose the log 1 over epsilon factor. Now, in the agnostic case, all we have to do is just replace epsilon with epsilon squared. And if we want to be more careful, actually, we can even replace this dimension of C here with some more data-dependent complexity measures, such as the Rademacher complexity or nil-DC entropy. And in the PAC model, one also very explicitly talks about efficient polynomial time algorithms for learning. All right, so this is all about supervised machine learning, which is a paradigm that operates under the assumption that humans can annotate all the data available for training, right? However, many modern machine learning applications have massive amounts of raw data. So for instance, protein sequences are currently acquired at industrial speed. There are billions of web pages on the web and huge collections of images as well, right? But clearly, humans can annotate only a very tiny fraction of all this. Right? This is why there has been tremendous effort in machine learning and its many application areas to design learning methods that most efficiently utilize the available data while minimizing the need for human intervention. And a modern paradigm, machine learning paradigm for doing so is semi-supervised learning, where in addition to labeled examples, the learning algorithm also uses raw or unlabeled examples as well. So a bit more formally, in the semi-supervised learning setting, the learning protocol is as follows. In addition to a set of labeled examples drawn random from the underlying data distribution, the learning algorithm also uses a usually much larger set of unlabeled examples drawn from the same distribution. All right, and this has been a really hot topic in the past 15 years in machine learning, and many different semi-supervised learning methods have been developed, such as transductive SVM, the co-training learning method, and various graph-based methods. Now, unfortunately, the classic learning models, like the PAC model and the statistical learning theory framework, are not helpful at all for thinking why unlabeled data is useful in the learning process. And while each of these methods had some theoretical justification, all the theoretical results are very scattered, and there was no general framework for thinking in a generic way about the fundamental principles underlying semi-supervised learning, and in which one can address questions such as when and why the unlabeled data can help and by how much. Right? So now in our work, we address this problem. And we provided a general discriminative PAC or statistical learning theory style for semi-supervised learning. And one of the main goals here in this work was to be able to incorporate in this framework the many different assumptions, taking the many different semi-supervised learning methods that have been proposed over the past 15 years in the machine learning community. So this is one of our main goals. Now, however, many of these different methods are based on very, very different assumptions about the data. And so this was really a key challenge that we had to address, how to incorporate in a unified way these very different assumptions that make unlabeled data informative. All right, and to be concrete, let me give you now two very different types of typical assumptions. The first one is the so-called large margin assumption. And it's an assumption that is used by the transductive SVM learning algorithm. And this is actually a very natural and very common assumption used in machine learning. And it says that not only should the target function, which in this case is a linear separator, so not only should the target function separate positive examples from negative examples, but it should do so by a large margin. And here I say that the separator has margin gamma if the probability mass within distance gamma of the separator is 0. And in this setting, under this assumption, unlabeled data is useful since, intuitively speaking, it can help us to throw out unreasonable hypotheses. So it can help us to throw out hypotheses that do not have a large margin. So for instance, in this example here, this dotted purple hypothesis will be thrown out if we are given a large enough unlabeled sample. All right? Now, a second, very different type of assumption that makes unlabeled data informative is the assumption of agreement between two parts, which is an assumption that underlies the co-training learning procedure. So in this setting, we assume that examples comes as pairs, and we are trying to learn a pair of functions. We are trying to learn a pair of functions. And so, for instance, imagine that we are trying to classify web pages, say as faculty members' home pages versus non-faculty members' home pages. This is the example in the original paper, that's why I'm using it. Right, so imagine that you want to do this classification problem. Then x1, so the first set of features could be given by the words inside the page itself, while x2 could be given by the words from the hyperlinks pointing to our web page from other pages. And the hope that underlies this co-training learning procedure is that the two parts of the examples are consistent. They agree on each example, and they are also, in principle, sufficient for correct classification. And this then allows us, in certain settings, to bootstrap by using unlabeled data. Because in principle, conceptually, we can just use unlabeled data to kind of propagate learned information. All right? So this is a second very different type of assumption that makes unlabeled data informative. It's very different from co-training. Now, going back to from the margin assumption, now going back to the more generic view, clearly standard models like statistical learning theory framework and the PAC model are not helpful at all for thinking about semi-supervised learning and why unlabeled data is useful at all in the semi-supervised learning context. And in particular, in these models, one usually talks about learning a concept class C usually under an unknown distribution D, sometimes under a known distribution D. But anyway, in these models, it's not clear at all what unlabeled data can do for us. And in fact, in these models, there is on purpose a complete disconnect between the target function and the underlying distribution. And unlabeled data doesn't give us any more information about which function in the class is more likely to be our target function. Okay? So these are really not useful for explaining the usefulness of unlabeled data in the semi-supervised learning setting. Now, the key insight of our model, because I mentioned we have a model, so the key insight of our model is that what makes unlabeled data so useful, so informative, and what many of the existing semi-supervised learning methods exploit, is that for certain problems, the natural regularities of the problem involve not only the form of the function being learned, say a linear separator, but also how that function relates to the underlying data distribution. For instance, it has a large margin. Right? And now, in order to talk about this formally, so what we do, we augment the notion of a concept class C, which is a set of functions like linear separators, decision trees, and so on. So augment the notion of a concept class C with a notion of compatibility between a concept and a data distribution. And then rather than talking about learning the class C, we'll be talking about learning the class C under compatibility notion chi. And really, through this notion of compatibility, we just express the belief, the relationship that we hope that the target function and the underlying distribution will possess. So for instance, suppose that we believe that there exists a good linear separator for our data, and that moreover, there exists a separator that has moreover, this separator has a large margin. Then what we want is a compatibility notion that penalizes functions like this one, the dot purple function here, that slice through high density regions of the space. All right? Now, given this setup, the main idea is to use unlabeled data and the belief that the target function is compatible in order to reduce the search space from the whole set of functions down to only those functions that are highly compatible functions in our class. And this is really the picture just for the realizable case, where the assumption really holds. In the non-realizable case, technically speaking, what we do data-dependent structural minimization by using our compatibility notion. And informally speaking, we just bias the learning algorithm towards the more highly compatible functions in our class. All right? Now, notice that we want to provide this reduction, obviously, by only using a finite sample, right? So we only want to use a finite unlabeled sample in order to provide this reduction or this biasing of our algorithm. And so, therefore, we also require that the degree of compatibility is something that can be estimated from a finite sample. Yeah? Right, so we want to provide this biasing by only using a finite sample, and moreover, also technically, we also wanted to be able to analyze how many unlabeled examples we need in order to estimate these compatibilities uniformly well. And so for both these reasons, we also require that the degree of compatibility is something that can be estimated from a finite sample. And the one very simple way to achieve this is just to require that the compatibility can be written as an expectation of our individual examples. So in other words, given a hypothesis H and an example X, chi of H and X is a score between 0 and 1. The closer to 1, the more likely is that our example X satisfies the compatibility assumption with respect to the separator H. And then the compatibility between H, hypothesis H and the distribution D is just the expected value over X drawn from D of chi of H and X. And then you can think of the incompatibility of a hypothesis H with the underlying distribution, which is 1 minus chi of H and D, as something like an unlabeled error rate. And I'm going to use this kind of terminology later in the talk.
So like for a large margin?
Yeah, this is perfect. So that's my next slide. Right, so for instance, if we go back to the large margin setting and we assume that our examples are points in our, say, in Rn, and the concept class that we are looking at is a class of linear separators, then if we know the margin gamma in advance, so if we know the margin gamma in advance, then we can define chi of H and X to be 1 if the point is farther away than distance gamma from the separator, and we can define it to be 0 otherwise. And with this definition, then, the incompatibility of hypothesis H with respect to the underlying distribution or the unlabeled error rate of our hypothesis is just the probability mass within distance gamma of the separator, which really nicely incorporates our belief of having a large margin. Okay? So this is for the case when we actually know the margin gamma. Now, in the case where we don't know the margin gamma, we can just define chi of H and X to be a smooth function of the distance to the separator. Now, right. Now, one thing that I want to point out is that on the other hand, a notion of compatibility that would be based on the largest gamma such that the separator has probability mass 0 within distance gamma of the separator, so that wouldn't fit our framework. It's something, because it cannot be written as an expectation of individual examples. In fact, it cannot be estimated from a finite sample. So that wouldn't be a robust notion of compatibility. We wouldn't want to use it. Right? Now we can also nicely incorporate in this framework the co-training assumption. And just to remind you, in the co-training setting, we assume that examples come as pairs, and the goal is to learn a pair of functions. And here the hope is that the two parts of the examples are consistent. And so, given this hope, then a natural notion of compatibility is to define the compatibility between a hypothesis H, which is a pair of functions H1 and H2, and the distribution D, to be just the probability that the two functions predict in the same way on an example drawn from our distribution. And then one can easily notice that this can be written as an expectation over individual examples. Yes?
So in the case with the transductive SVM,
yeah,
you can look at this agreement function itself as being some function in terms of its generalization abilities, right?
What do you mean by agreement function?
Well, so if your function is like the mapping from the given a hypothesis, given the data point, ignoring its label,
yeah,
you'll value the data point as...
Yeah, this is exactly the compatibility, yeah.
So you can look at this itself as a function which has some, you're trying to figure out its generalization ability of how,
but
you have an empirical average for each hypothesis.
But it doesn't depend. Okay, so that's right. This is basically a compatibility, right? For each function, you can define an unlabeled error rate, right? This is what exactly we do.
You could look at, the worst case overall of this hypothesis class of how far the empirical, agreement rate is compared to, the true error rate, right?
I mean, you can estimate the compatibility or the unlabeled error rate based on unlabeled data. Yes.
Right. So my question is actually, so for the half space example for this transductive SVM,
yeah,
this error rate actually looks like sort of two parallel. It's like a smooth version of two parallel half spaces, right? Because you penalize things which are further, which are closer in. So
yeah.
it ends up mapping something which is like constant VC dimension, the VC dimension bound for the half space, to something else which also has bounded VC dimension.
Right. Okay. So actually, I think once I go through my you see. So actually, right. So basically,
is that true in general? I'm just curious. Like, will this be true for co-training too, or?
Right. So actually, right. What we are talking about is how many examples do we need in order to estimate unlabeled error rates well. This is what we are talking about, and we analyze this generically, and I'll be precise about it.
Okay.
So this is really what we are asking. Right, and so so now given this generic framework, right, we can now analyze generically fundamental sample complexity results. And for instance, one type of statement that one type of question that we can address is how much unlabeled data do we need in order to estimate compatibilities or unlabeled error rates uniformly well. And this is your question, related to your question. This is one thing that we can analyze. We can also analyze the ability of unlabeled data to reduce dependence on the number of labeled examples. Yeah, this is obviously another very important thing that we want to analyze. And I'm going to actually give examples of such sample complexity statements in a slide. Now, I want to point out, before I go on, that as I mentioned earlier, in the PAC setting, one talks either about the realizable case, where we assume that the target function itself is in the concept class, or about the unrealizable case, where we don't assume that the target function itself is in the concept class. This is the agnostic case. Now, in our setting, we have an additional issues of unlabeled error rate. And we can either make the assumption that the target function is small unlabeled error rate, or is very compatible, or otherwise just provide the bound on the number of labeled examples that depends on whatever the unlabeled error rate of the target function happens to be. So now we have 4 cases as opposed to 2. All right, and actually let me give you an example of a simple sample complexity statement that illustrates this framework. This is a uniform convergence sample complexity statement for the case where C is finite, and that is really meaningful for the doubly realizable case. This is a case where the target function has 0 labeled error rate and is perfectly compatible, has 0 unlabeled error rate as well. And now what we can say is, for instance, if the number of unlabeled examples is roughly 1 over epsilon log of size of C, and if the number of labeled examples is roughly 1 over epsilon log of the size of the class of functions whose true unlabeled error rate is at most epsilon, or true incompatibility is at least or minus epsilon. So if we see so many unlabeled examples and so many labeled examples, then with high probability, all the hypotheses that have empirical labeled error rate 0 and empirical unlabeled error rate 0, so all the hypotheses that agree with the labeled sample and also are compatible with the unlabeled sample, have true error rate, labeled error rate at most epsilon. All right, so this basically provides a guarantee for an algorithm that picks hypotheses that perfectly agrees with the labeled data and is perfectly compatible with the unlabeled data. All right, and since the proof is really simple, I'm just going to quickly go through it. First of all, we can say that if we fix a hypothesis H, the probability that of true unlabeled error rate at least epsilon, the probability that our hypothesis H is compatible with the unlabeled sample is at most 1 minus epsilon to the mu, where mu is the number of unlabeled examples, which our choice is most delta over 2 times size of C. So this is for any fixed hypothesis H. Then by just doing a union bound, we get that with probability at least 1 minus delta over 2, only the functions in this set CD chi of epsilon, so only functions whose true unlabeled error rate is at most epsilon are compatible with the unlabeled sample. And then we can just again do a similar argument. We can show that ML is large enough, so the number of labeled examples now is large enough in order to ensure that none of the functions in this set, none of the functions have true unlabeled error rate at most epsilon, but also have true labeled error rate at least epsilon, have an empirical labeled error rate of 0. Okay, and using this fact we then just get the desired result. Okay, so the proof is very simple, it's not important. What's interesting here is to notice that the number of unlabeled examples in our framework matches the number of labeled examples in the usual supervised learning setting. However, the number of labeled examples can be much smaller than what you need for learning in the supervised models like PAC, statistical learning theory framework. And in particular here, the number of labeled examples is a distribution-dependent quantity. And so actually you can think of this bound on the number of labeled examples as a measure of the helpfulness of our distribution with respect to our notion of compatibility. So helpful distribution will be one where this quantity is small, and non-helpful one obviously will be one where this quantity is large. So for instance, here is an example of a helpful distribution for the large margin setting, where we have just two very well separated blobs. This is a less helpful distribution for this large margin setting. All right, and then we can also, so this is the sample complexity statement for the simplest possible case. We can also get now more interesting sample complexity statements for other cases as well. Just quickly to go through it. So for instance, in the case where the class of functions that we are looking at is not finite, and in the case where the target function is not necessarily fully compatible, so it doesn't have unlabeled error rate 0, then what we can show is that if the number of unlabeled examples is roughly VC dimension of chi of C over epsilon squared, where chi of C is a class of functions induced both by our concept class C and by our notion of compatibility, right? So if we see so many unlabeled examples, and then if the number of labeled examples is roughly 1 over epsilon times the expected number of ways to split 2 ML points from our distributions with concepts from the class of functions whose true unlabeled error rate is at most t plus 2 epsilon. So if we see so many unlabeled examples and so many labeled examples, then with high probability, all the hypotheses of true of empirical labeled error rate 0, of empirical unlabeled error rate at most t plus 2 epsilon, have true labeled error rate at most epsilon. So in particular, for instance, if the target function has unlabeled error rate at most t, then this algorithm provides a guarantee on an algorithm that picks a function, an algorithm that minimizes the empirical unlabeled error rate subject to agreeing with the sample. And when the guarantee we have it, that algorithm outputs a hypothesis of true error at most epsilon. Right? So, by the way, the details here are not so important. I just want to actually, in words, point out, in case this looks too complicated, I just want to point out in words some of the interesting aspects that actually appear when we talk about sample complexity statements in these more interesting, more general cases. So the first interesting aspect that appears is that in order to estimate compatibilities uniformly well, we have to or the unlabeled error rates uniformly well, we have to take into account both the complexity of our concept class C and the complexity of our notion of compatibility. Right? Because we could obviously have a very simple concept class like threshold on the line, but an incredibly complicated notion of compatibility, so we need lots of unlabeled examples to estimate compatibilities uniformly well. Okay, this is the first issue that appears. Now the second and perhaps the most interesting issue here is that when on our bound on the number of labeled examples, we really want to use a distribution-dependent measure of complexity. So in particular, like an yield VC entropy, this is what I'm using here, or Rademacher complexity. And in particular, VC dimension is not a good measure of complexity for this case. Because for instance, going back to the large margin setting, even if we have, say, two very separated blobs, right, then still the VC dimension of the functions with very high compatibility is still as large as the VC dimension of the original space. So it's not good. On the other hand, all those functions that have very high compatibility are very similar to each other. And the more data-dependent notion of complexity, like an yield VC entropy, will provide us much better bounds, so it'll be a constant. So it's really important to use here distribution-dependent measure of complexity when quantifying the number of labeled examples. Kind of much more crucial than in the supervised learning setting. All right, so this is about uniform convergence type of result. Now, I also want to mention that actually in our work, we also looked at epsilon cover-based bounds. And it turns out that these bounds provide a much better, sometimes they provide a much tighter bounds than uniform convergence bounds. And now these bounds only work for more specific algorithms that behave in a specific way, where we first use unlabeled data to choose a representative set of compatible hypotheses, and then use labeled examples just to choose among those. Okay, and it turns out that in certain cases, these epsilon cover-based bounds are drastically better than the uniform convergence bounds in the semi-supervised learning setting. And we give concrete examples in our work. Now, obviously, I guess the algorithmic problem here becomes harder actually. So the bounds are potentially much tighter, like you can go from 1 over epsilon to 1 labeled example in certain cases. But the algorithmic problem becomes much harder. And actually in our work we also give an interesting algorithm for an interesting case where you can achieve in polynomial time the epsilon cover-based bounds. But I guess it's an open question in general to make this epsilon cover, to come up with general algorithm based on epsilon cover-based bounds that are also polynomial time. All right. So I guess to summarize, so worst case models like PAC or statistical learning theory framework are simply not useful at all for talking about the usefulness of unlabeled data in semi-supervised learning, and which is a very important modern machine learning paradigm. And in order to address this, in our work, we develop a new model for semi-supervised learning. And in this model, we can now analyze fundamental sample complexity aspects, such as how much unlabeled data do we need in order to learn well. And actually, as I mentioned, this turns out to depend both on the complexity of our concept class C and on the complexity of our notion of compatibility. Okay, so this is one fundamental question that we address. We also are able to quantify the ability of unlabeled data to reduce dependence on the number of labeled examples. And this turns out to depend both on the compatibility of the target function and on the helpfulness of our distribution. And in particular, it turns out that in this semi-supervised learning setting, unlabeled data is helpful if the target function is compatible, and moreover, if the complexity of the class of functions that are as compatible as the target function is small. And as I mentioned, we also analyze both uniform convergence and epsilon cover-based bounds. The epsilon cover-based bounds are much tighter. Often, however, the algorithmic problem becomes harder here. And I guess this is a more practical comment actually. Interestingly, our analysis suggests better ways to do regularization based on unlabeled data. So this is something that people have been doing empirically. Our analysis suggests improved way to get better sample complexity results to learn with even fewer labeled examples. All right, and I guess I just want to finally also mention that actually subsequently to our work, so this framework has been used both for analyzing existing semi-supervised learning algorithms and also for designing new learning algorithms. And actually this work is part of a book chapter on semi-supervised learning. It was published a couple of years back. And the interesting fact is that we can use this framework to analyze all the different methods in that book, all the different semi-supervised learning methods in that book. So it's pretty general. All right, thank you. Questions?
Questions for you?
The case where the learner gets to ask for the labels of specific things?
So that's a great question. That model is called active learning, and I've actually done a lot of work on active learning as well. So sure, I mean you can combine the two models, obviously. You could combine the two models. The traditional analysis of active learning has been just without any compatibility assumption, without any extra belief. So that has been the traditional analysis of active learning, but obviously we can combine the two models. Like you could have an extra belief and be active. Yeah, then see. Obviously this will give you much more power being active sometimes.
So in terms of practice, you said that the size of the compatibility can be much lower than
Yeah.
space. So how much lower? Like 10 times lower?
So that's the point. Depends on how much the underlying distribution satisfies your assumption with respect to the target function. So it's not, it's really a data-dependent quantity. So yeah, it just depends on the data set. I cannot give you a generic answer.
Yeah, it's not killer application of it.
So I did not do, I did not implement any, I mean, this is, I did not do any empirical work here myself, but all this model is, but there has been a whole community, right, in machine learning and application areas, where they have all these methods that I talked about, conductive SVM, code training, and graph-based methods. They have been implemented and analyzed on many different types of data sets. Right, and in different data sets, they can get a drastic improvement. So it really depends on the specific application. Right, what was lacking prior to our work, so people had came up with these methods, and they were noticing, oh, sometimes it helps. Look, we get 100 times improvement, or we get significantly greater improvement, but they had no language, no way of expressing why do you get the improvement. And there was no way of talking why is unlabeled data helpful. And so this is really the focus of this work, to try to develop a model that allows you to reason about this formally, and then hopefully helps to guide you to new learning procedures, to better improve learning procedures. Right, and actually in particular, as I said, this really suggests a better way. The framework itself suggests a better way to design semi-supervised learning methods than what people have done in practice. Yes?
Are the bounds high enough here? I know in some of the worst case models, the PAC bounds are not very high. But
right, so this is what I'm saying. For instance, if you go back to this slide, yeah, so we try to, on the number of, okay, first of all, you do not optimize the bounds on the number of unlabeled examples. So you're just happy with polynomial in the relevant quantities. Of course, you can also do data dependent here. But in the number of, in terms of the bounds and the number of labeled examples, we try to make them as tight as possible. And as I explained, in order to do this, we really need to use this distribution dependent notion of complexity. And they are, to some extent, as tight as they can be.
Okay, so is there enough difference between the bounds for different types of algorithms? So for instance, what I wanted to know is there something here to help you choose between like transductive SVM and co-training on a specific class of instances?
So, well, I guess one thing you can do, you can run the two algorithms in parallel, and somehow, okay, I do not have this on the slides, but you can, right, you can kind of, right, you can run the two algorithms in parallel and kind of, for each of them, just stop when you have enough label data to kind of justify the hypothesis produced. And then, of course, right, so...
If I have a week until it does, and I don't want to know after the thing's going to take 7 days to run, is there any way to necessarily use an analysis under this to tell me whether I should start with transductive SVM or co-training or some other S?
Well, okay, so this goes, okay, so in any learning problem, so semi-supervised or supervised, in order to be able to do any type of learning, you need to have some biases, called some bias. You need to have some assumption about your data. If you have no belief about the data, there is no way to get generalization. Right? So in any learning problem, you have to have some assumption. Right? And so...
To use the compatibility, so I know the distribution of my data, is there enough difference between the compatibility measures?
Sure, it can be very different, right? So, right, conductive SVM might work sometimes, and code training might not work, and the other way around, right? And it's obviously, or graph-based methods might work sometimes, right? But it's all not just difference, right? If you ask me how to pick, okay, so I'm telling you that there is a theoretical way to pick, or you run the two of them in parallel, so kind of you run both conductive SVM and code training in parallel, and you stop for the first of them for which you have enough, so the bounds will tell you when you have enough label data to justify the hypothesis produced, so you know for which one to stop first. This is something you can do for sure. But if you have a week before the deadline, then you really have to rely on your intuition and on your bias about the problem. So, but again, that's inherent in any learning problem. You know, if you don't want to run in parallel algorithms, right? This is the first method that I proposed. If you don't want to do that and just run one of them, then you really need to use your kind of belief about the problem.
So this compatibility help. Suppose I can just calculate the compatibility of the back of the book between these different SSL. Compatibility is a good guide.
Yeah, your belief. So the compatibility expresses your belief, right? Do I have a large margin? Maybe you want to run on data and you know that it's related to some other types of data with a large margin. Maybe you believe that large margin is the appropriate compatibility notion to go for. Or maybe you have disagreement between two parts, then you go with code training. Or if you believe that you're, like in the graph-based method, you believe that nearby examples have similar label, you use a graph-based method, right? So you need to have some belief in order to choose this, or alternative, you can run them in parallel and you know where to stop.
All right, let's thank you again.